Hello everyone. In this video, let's learn how we can design a finite state machine which detects a sequence of 0010 in a serial input. And then also let's draw the circuit using D flip-flops. So what is a finite state machine? It's another name of sequential circuit. It gives us information that if an input is applied on one state, what will be the next state and what will be the output. So let's get right into it. The first step is to draw the state graph. So since we have to detect 0010, so 0010, that means we need 4 states. So let's call the states S0, S1, S2, and S3. And then for S0 it will be 00, for S1 it will be 01, S2 it will be 10, and then S3 will be 11. So let's start. At S0, if we apply an input of 0, so this takes us to the next state S1. And then the output will be 0. So this will be the input. Let's call it I. Or let's call it X. And then this will be the output. Let's call it Z. And then at S1, if we apply 0 again, so this also will take us to the next state. So from S1, if we apply an input of 0, the output will be 0, and then we'll be at state S2. At S2, if we apply an input of 1, which is the third bit here, so we'll go to the next state, which is S3. And here we applied an input of 1, and the output will be 0. And at S3, if we apply the fourth bit, which is 0, so where should we go? From S0 to S1, if we apply 0, we go to S1. So here, if we apply 0 here, so the output will be 1, but we'll go to S1, because we detect 0 as well. So we'll go from S3 to S1, we apply 0, and then the output will be 1, because we completed the sequence. Think of it as if you're entering a passcode for your phone, 0010. If you enter it in the sequence of 0010, you will unlock the phone, so the output will be 1. Now let's see what happens if we enter the wrong bit. So at S0, if we enter 1 instead of 0, what will happen? We will stay in the same state. So if we enter 1 here, the output will be 0, but will be at the same state. So at S1, let's assume we enter, instead of 0, we enter 1, the wrong bit. So this will have 0, 1. So 0, 1 is wrong. So we go back to S0. So from S1, if we enter the wrong bit, which is 1, we go back to S0 and the output will be 0. So at S2, if we enter the wrong bit, the correct bit is 1. But if we enter 0, so we have from S0 to S1, we have 0. From S1 to S2, we have another 0. And then let's see we enter the wrong bit, which is 0. So what happened at S2? We just discard one of the zeros, so we stay in the same state. So if we enter 0 here, we stay in S2, and then the output will be 0. Now let's assume we are at S3, and then we have 0, 0, 1, and then at S3 we're supposed to enter 0. But let's assume we enter the wrong bit. We enter 1 instead of 0. So 0, 0, 1, 1 is fully wrong. It doesn't match anything in the original code 0, 0, 1, 0. So that means we will discard everything and go back to S0, to the initial state. So from S3 we go back to S0 if we apply an input of 1, and then the output will be 0, of course. So this will be the state graph. The next step is to design the state table. So now let's do the state table. So we have the current state. Let's call them, because we have 2 bits, let's call the current state Q1, and Q0. And then we have an input X. And now we want to know what will be the next state. So let's call the next state Q1 plus, Q0 plus, and then we have the output Z. So S0 is 0, 0. And then our input could be 0 and could be 1. So let's write it again. So this is belong to S0. And now the next state is S1. S1 is 0, 1. Also, we could enter an input of 0 and an input of 1. So let's write the state twice. This is S1. Next, we have S2. S2 is 1, 0. Also, same idea. The input could be 0. We could enter 1 as well. So we write it twice, 1, 0. This is S2. And then lastly, we have S3, which is 1, 1. And then the input, we could enter 0 or we could enter 1. So let's write it again, 1, 1. So this will be S3. Now let's check the next state. So we are in S0, 0, 0. If we enter 0, so we can check in the state graph. If we enter 0, we go to the next state, S1. And S1 is 0, 1. So that's why we write on the next state, we write 0, 1. And then the output Z or Z will be 0. Now if we are in S0, but we enter an input of 1, looking in our state graph, we stay in the same state. So the next state will be 0, 0, same as the current state, and then the output will be 0. So next we are in S1, which is 0, 1. And what happened when we apply an input of 0? So we go from S1 to S2, and the output will be 0. So the next state will be S2, and S2 is 1, 0. And the output is 0. Next we are in S1, but we enter an input of 1. So where do we go? Look in our state graph, we are in S1, we enter an input of 1, so we go back to S0. S0 is 0, 0, and then the output is 0. Next we are in S2, and we enter an input of 0. So we stay in the same state, S2. And S2 is 1, 0. So next state will be 1, 0, and the output will be 0. Next we are in S2, and then we enter an input of 1. So that means we go to the next state, S3, and the output will be 0. So the next state, S3, is 1, 1, and then the output is 0. Next we are in S3, 1, 1, and then we enter an input of 0. So this will be the transition from S3 to S1, and then the output is 1. So S1 is 0, 1, and then the output will be 1. Now we are in S3, 1, 1, and we enter an input of 1. So that means we go back to S0, and then the output will be 0. So the next state will be S0, which is 0, 0, and then the output is 0. So that's it for part 1. Now for part 2, it says draw the circuit using D flip-flops. So for D flip-flop, let's have an overview of what D flip-flop is. We have an input D, and then we have a clock. That's for rising edge D flip-flop. This is the clock. And then we have an output Q and Q prime or Q bar. And then the state or truth table for D flip-flop, we have D, Q is the current state, and Q plus is the next state. So if D is 0 and the current state is 0, so the next state will be 0. If D is 0 and the current state is 1, the next state will be 0. If D is 1 and the current state is 0, the next state will be 1. If D is 1 and the current state is 1, the next state will be 1. So looking at Q plus and D, they are equal. So D equal Q plus and D flip-flops. So now we can go back to our state table and add the inputs for two. We need 2 D flip-flops to design the circuit. And then how we know? So the number of flip-flops is equal to log 2 of the number of states. And then in this example, we have 4 states. So log 2 of 4 will be 2. So that means we need 2 flip-flops. So let's assume the first input of the first D flip-flop is D1, and then D0 is another input for the second D flip-flop. So D1 will be equal to Q1 plus, and D0 will be equal to Q0 plus. So we can simply write these two. So for D1, we'll have 0, 0, 1, 0. So next we can use K-map to obtain the Boolean function for D1 and D0 so we can design the circuit. So for D1, we need to write it as a function of Q1, Q0, and user input X. So that means we need a 3-variable K-map. So we can design it this way. Then we have, on this side, we have a Q1, and then on this side, we can use Q0 and X. For Q1, 0, 1. For Q0X, we have 0, 0, 0, 1, 1, 1, and 1, 0. So next, we look at D1 when it's 1, but we look at the current state, Q1, Q0, and user input X. So let's start at this one. So we have 1 for Q1, Q0X of 0, 1, 0. So that's 0, 1, 0. So we'll have 1 here. And then another one at 1, 0, 0. So that's 1, 0, 0. So we'll have another one here. And also we have another one at 1, 0, 1. So that's 1, 0, 1. So we'll have 1 in this location. So that's 1. And then the rest are zeros. Now let's do the grouping. We can group these two together, and then this one will remain by itself. So from this group, we get Q1, Q0 bar, or Q0 prime. We discussed K-maps in previous videos, so you can refer back to it if you're struggling with this K-map. For 1, we have Q1 bar, or Q1 prime, Q0 prime, actually Q0, and X prime. So now we can write the Boolean function for D1. D1 will be equal to Q1, Q0 prime, plus Q1 prime, Q0, X prime. So next, let's do the same for D0. So for D0, also we need to write it as a function of Q1, Q0, and X. So on this side, we'll have Q1, Q0, and X. So we have 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. So let's look at when D0 is 1. So we have 1 in this location. So that's for 0, 0, 0. So 0, 0, 0. We have 1 here. We have 1 in this location, which corresponds to 1, 0, 1. So that's 1, 0, 1. So we'll have 1 here. And then lastly, we have 1 corresponds to 1, 1, 0. So that's 1, 1, 0 is in this location. So the rest will be zeros. For this one, we cannot group any ones together, so they have to remain separate. So for this one, we will have Q1, Q0, X prime. For this one here, we will have Q1, Q0 prime, and X. And then for this one here, we will have Q1 prime, Q0 prime, and X prime. So now we can write the Boolean expression for D0. So D0 will be equal the summation of these three. Q1 prime, Q0 prime, X prime, plus Q1, Q0 prime X, plus Q1, Q0, and X prime or X bar. So that's it. Now we can design the circuit. And the output, if we look at the output Z, is equal to Q1, Q0, X bar. So Z is equal to Q1, Q0, and X bar or X prime. Now we can take these three equations and design the digital circuit. So let's do that. So we'll use two flip-flops, D flip-flops. So D1 has an input D1 and it has a clock, let's call it CK, and then has two outputs, Q1 and a Q1 prime. And then for the second D flip-flop, we have an input of D0, and then also we have a clock, and then we have two outputs, Q0 and a Q0 bar or prime. So for D1, we need an OR gate because we have summation, so that's an OR gate. And then we have two terms multiplied by each other, so we need two AND gate. So from here, we need an AND gate. And then also we need another AND gate. And then one of them, we need to feed Q1, Q0 prime. So where do we get them? We get them from here. So we have a Q1 will be one input to this AND gate. And then a Q0 prime, we get it from this D flip-flop. So this will be the other input for this AND gate. And then for the second one, we need Q1 prime, Q0, and X. So we can get them Q1 prime, we can get it from here. So we can get Q1 bar. We also need a Q0. We can take Q0 from here. And also we need user input X. What we need to do to get X bar. So we can use a NOT gate. And this is our X user input. So this is, we're done with D1. Now for D0, same idea. So let's write it here. We need an OR gate. And since we have 3 terms, so we need 3 AND gates fed into the OR gate. So we need one AND gate, another one, and then a third one. So for the first one, let's start with this term, Q1 bar, Q0 bar, and X bar. So same idea, we can get Q0 from here, bar. We need also Q1 prime, so we can get it from here. And then X is a user input. But we need X bar, so we can use an inverter and then feed the user input in it. For the second one, we need the Q1, Q0 bar, and X. So same idea, we know where to get them from. Let's just like write it like this, Q1, Q0 bar, and X. And then for the last one, we need the Q1, Q0, and X bar. Also same idea, we know where to get them from. So that's Q1, Q0, and user input X bar. So that's it. Thanks for watching. I hope this was helpful in the Finite State Machine, FSM.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.